Okay, so in this lecture, we'll try to explain in detail why data structure is important and when we actually learn data structures and how we actually learn data structure. So first thing first, so this will be covering the basics of data structure. So what is data structure? The logical or mathematical model of a particular organization of data. Data structure stores the data. So data can be an integer, it can be a string, it can be float. Data structure can answer question about the stored data. Example, what data is stored at the position I. So you can actually get a data from position number 5, position number 6, and so on. What is the smallest data value greater than or equal to X? You can actually find that. You can add or remove data from some data structures. So data structure stores the data, can answer questions about the stored data, can add or remove data. Why study data structure? Data structure examples, there are some example applications like computer file system. We use data structures to map file names onto hard drive sectors. Google and other search engines, they use data structure map keywords onto web pages. So whenever you search something on Google, they can actually, you can see millions, billions of results within a 1 second of time. So that because all the data is stored and retrieved efficiently. How can a subsequence of DNA can be quickly found with a genome? This is an advanced application of data structure. Geographic systems, data structure find data relevant to the current view or location. Then finding large prime numbers from smallest to the largest, we need data structure, and so on. Many problems are solved efficiently just by using the right data structure. That's the main point you have to know. That's why we actually study data structure. If you can use the correct data structure, many of your programs actually get solved within a very short amount of time and very, very efficiently. So that's why we actually study the data structure. Now, when should we study the data structure? If you are students of computer science, you should study learning data structure as soon as possible. As soon as you have a basic understanding of 1 or 2 programming languages, okay, you should actually learn data structure, and you should continue for the rest of your life, okay, as much as you can learn. Data structure, learning data structure always helps. Knowing the right data structure, you can help impress your boss, give your software an advantage over your competitors. Okay, because if you know the proper data structures and algorithms, you can actually make your softwares more efficient in terms of speed and other criteria, which will give you an advantage. It can save you a lot of work and allow you to make new scientific breakthroughs. So you should learn data structure as soon as possible and as much as you can. Now, let's talk about some terms related to data structure. First of all, memory allocation. What is a memory allocation? Memory allocation can be classified as contiguous, linked, and index. Whenever you allocate memory from your hard disk or the main memory, okay, there is 3 ways you can actually allocate the memory. One is contiguous, another is linked, another is index. So prototypical examples, contiguous allocation are done in array. So you are already familiar with arrays. So that is called a contiguous allocation, and linked allocation is done in linked list. We'll be discussing both of these data structures, how they store data very soon. So what do I understand by contiguous data structure? It's an adjective. It means touching or connected throughout an unknown broken sequence. That means if you allocate memory using contiguous allocation just like an array, all the memories will be touching each other or be connected with each other throughout an unbroken sequence. So in terms of computer science, it means actually next in space or meeting at a common boundary. So within a common boundary, they will be next to each other. So here is an example of contiguous allocation. So let's assume you have an array store n objects in a single contiguous space of memory. So unfortunately, you see here we have 1, 2, 3, 4, 5, 6, 7, 8 memory. And Here first 5 is taken. Okay, now unfortunately, if more memory is required, a request for new memory usually requires copying all this information to the new memory. That is a disadvantage of contiguous memory. In general, you cannot request for the operating system to allocate you the next n memory location. In linked list, okay, the storage such as linked associates two pieces of data which each other being stored. That means suppose if there is a object A and there's an object B, object A will point to object B will point to the next object, and in that way there will be a link between them. So this is called linked allocation. Don't worry if you are still not clear about the contiguous and linked. In the next lectures we'll actually discuss them in details, then you'll have the clear picture about how they're actually being stored. Just now we're trying to get an idea about them. Next, so this is an example of linked list. So for a linked list, however, we also require an object which links to the first object. That means, as I said, a linked list is actually a list with each object point to the next object. So A points to B, B points to C, C points to the next object, and if there is no other next object, it points to null. But the problem is, as we know that array starts from 0 and goes up to n. Okay, in the linked case of linked list, okay, it's dynamic. Okay, so it's the list kind of like this. It whenever you add more data, it automatically increases. Whenever you remove elements from the list, it automatically decreases. That's why you call it dynamic. In case of array, if you declare an array of n elements, you can only store n number of elements there. Okay, you can store less than n, but you cannot store more than n. In case of linked list, you don't have to actually declare any memory in before. Okay, you just have to create the linked list. You have to keep a head, keep a tail. Head will point to the start of the linked list, tail will point to the tail of the linked list. And you also can keep a count, it's optional. And what will happen, as soon as you can add as much as nodes or values in the list, and the list will automatically increase. You don't have to declare change the size of the list every time. It will automatically do that for you. Now, indexed allocation is the third option, if you remember. So in indexed allocation, an array of pointers which can be null linked to a sequence of allocated memory locations. So you see, this is actually array, and each of them actually point to a sequence of memory locations. This is actually used in C++ STL, standard template library, that we were just discussing in the previous video. And computer engineering students will see index allocation in their operating system course. So if you're doing the operating system course, there you will actually talk about details about indexed allocation. And here we will, in the hashing, we'll also talk about indexed allocation. So let's just give you some examples so that you can understand betterly. So suppose this is a matrix. This matrix is 1, 2, 3, 4, 5, 6. So if I want to implement this matrix or store this matrix using index allocation, there are two ways I can do that. So let's suppose this is my array of pointers. So if I want to store using rows, okay, so this is, these are the rows and these are the columns. So we have 2 rows and 3 columns. So if I want to store by rows, so first row will be stored in here. So you see 1, 2, 3. The first row is stored here. The second row is stored in the next pointer, 4, 5, 6. So this is one way of indexed allocation. So if there is another row, we can actually keep growing here. If I want to store by columns, so you see first column is stored in 1, 4. Second column, that is 2, 5, is stored here. Third column is stored is 3, 6. So there's both way you can do it. It's up to you. So most implementation of matrix or higher dimensional arrays use indices pointing to a single contiguous block of memory. So instead of taking a separate arrays, okay, or block of memories, what you can do, you can actually take a single array, and in that single array, especially in C and Python, we use the row major order. So that means first row will be stored sequentially, and after that the second row will be pointed by the same, stored in the same memory, and be pointed by the second index. Okay, so all these are actually indexes. This is the first index pointing to the first row. This is the second index pointing to the second row. Or we can do it in MATLAB or Fortran. We can use column measure order, where first row actually points to the first index actually points to the first column, second index points to the second column, and third row points to the third column. Let's go back again. You see, we're using index allocation. Okay, we can use separate block of memories, or we can use same array or same single contiguous block of memory. So these are index allocation. Now, what are the other allocation format? We have seen arrays, we have seen linked list, we have seen index allocation, some other trees, graphs, and DQ. So what is a tree? A tree can be also implemented in this way. So as you can see, the linked list can be used to store linearly ordered data. So what do you understand by linearly order? That means they're sequential in a linear fashion. And what if we have multiple next pointers? So we'll discuss it in the upcoming lectures. So in general, it will look something like this. It will start with A and then B, C. It's almost like a tree. Okay, it's like it's growing under. Okay. A rooted tree is similar to a linked list, but with multiple next pointers. That means normally in a linked list, as you can see, A points to B, B points to C, C points to null. So what is null? When a linked list have no other elements, is null. And head means the start of the linked list. In the tree, okay, we start with A, which pointing to B, and at the same time, it's pointing to E. B is pointing to C and B is pointing to D. So a rooted tree is similar to a linked list because it's also pointing to some values, but with multiple next pointers. That means it can point to multiple values. A tree is a variation of a linked list. Each node points to an arbitrary number of subsequent nodes. That means it can point to one node, it can point to two nodes, or it can point to more than two nodes. In the last picture, it is pointing to two nodes. Useful for storing hierarchical data. We will see that it is also useful for storing sorted data. Usually we will restrict ourselves to trees where each node points at most two other nodes. Okay, we can call them binary tree. So we will be learning, or we'll be focused on trees that have only points to two multiple next pointers. Then we have graphs. Suppose we allow arbitrary relationship between any two objects in a container. For example, consider the network. Okay, so let's assume B is a person. B knows F, G, A, J, C. C is another person who knows K, H, D, L, G, B, but C doesn't know J. Again, B doesn't know K. So this is actually a network of people who have, or you can actually tell this is actually roads. This is city A, this is city B, this is city C, this is city H. These are roads among them. Okay, so whenever you are trying to actually represent some arbitrary relationship or a network, we use graphs. Arrays are actually not that much efficient in terms of these relationships. And we can also try to implement the array, but as you can see, in this network is implemented here using an array. So the array representation, this is the array representation, and this is the graph representation. So we could represent this using a two-dimensional array. So this matrix has to be symmetric. That means you see A, B, C, D, E, F, G, H, I, J, K, L. At the same time, in the column, we have A, B, C, D, E, F, G, H, I, J, K, L. So let me explain what this matrix means. So first of all, let's focus here. This is A, right? So from A, we have row to F, we have row to B, we have row to J. So this is A. From A, we have a cross sign in B, we have a cross sign in F, we have a cross sign in J. So that means with A, we have a connection with B, we have a connection with F, we have a connection with J. Rest of the array values are kept null. Same, let's try for another one. Let's assume C. With C, we have a connection to B, we have a connection with K, we have a connection with L, D, H, and G. So from C, we have a connection with B, D, J, H, K, L. So in this way, we actually represent all the relationship in an array using a two-dimensional array. And we can also use arbitrary relationship between any two objects in a container. Like we can use a hybrid array of linked list to represent this relationship. So from A, we have a connection with, you see, again, from A, we have a connection to B, F, J. So we can say, write this. This is an index. From A, we have a connection with B, F, J, and null. Then we have B. So with B, you have connection to F, A, J, C, G. So from B, we have A, F, J, C. And this way, okay, try to actually compare all of this so you'll get the full picture. So what I'm trying to show that there are different ways you can actually store the data. And sometimes you can actually use a hybrid way. Okay, you can combine linked list with indexes. You can combine linked list with array. Okay, you can combine graphs and array. It actually depends on what is your problem statement. Depending on different problem statement, we actually use different approaches to efficiently solve a problem. So eventually we will actually discuss all of this in the upcoming lectures, and eventually you will actually get the idea that if I see this type of problems, I have to use this type of data structure. And what are the operation of data structures? In a data structure, we have these operations: traversing, that means traveling the data; searching a specific data; inserting a data; deletion of a data; sorting the data; and merging the data. So what does traveling means? You get to search, you get to travel the data, what data you have. If I go to the last picture, you see here B, F, J, we can see B is connected with A, F, C, J. So this is kind of a traveling. Searching means if I ask you that find what are the connections on in the C network. So, or I may ask you that is C and L is connected, then what you have to do, you have to first go to C and you have to check, is there any road between C and L? So you see there's a road between C and L. So this is called searching. Then inserting, if we want to add a new connection between F and J, this will be called inserting. Then deletion, if you want to delete the road between F and B, this will be called deletion. So you have to go to F and you have to remove this B. Then sorting, what does sorting means? If you want to sort them, you see all of this B, F, G, they're actually sorted. That means the smaller one comes first, A, B, C, D in a alphabetical order. And then merging, if you want to merge these two lists, okay, if you want to combine these two rows, this can be called merging. So we'll see more details, but the question is, how do we determine the efficiency of algorithms? So which one is, from the beginning of the lecture, I'm saying that this is more efficient, this is more efficient. So how we can actually understand the efficiency of the algorithm? So to understand the efficiency, we actually use a term called complexity analysis. There are two ways we can actually compute the complexity. One is called time complexity, another is called space complexity. So we'll actually see that the complexity of the algorithm is the function which gives the running time or the space in terms of input size. That means how many time it takes to run a code or how much memory it takes to run a program. By increasing the amount of space for storing the data, we might be able to reduce the time, or by increasing the time to process the data, we might actually decrease the amount of memory it needs. So this is called time space trade-off between time and space complexity. So we'll discuss this in the upcoming lectures. So in short, let's just go from beginning. First, we discussed the basic, what is data structure, why we need to learn data structures, how we actually need to data structures, then when we should start learning data structure. Then we have discussed some memory allocation techniques. It started from contiguous memory allocation like array, linked allocation like linked list, then indexed allocations like this ones. And then we have talked about some other formats like trees, graphs, and DQs. We have seen that we can actually sometimes use the hybrid method, okay, to implement some represent some data. Then we have talked about the 6 operations of data structures. And finally, you have talked about that there are ways we can actually find the efficiency of an algorithm. So that will be